Hi, my name is Nishan Subedi. I work at Overstock, and I'm here to present work with my colleagues Chen Wang from Rutgers University and Aidan on the machine learning ranking team at Overstock on making rewards more rewarding via sequential learnable environments for deep reinforcement learning based sponsored ranking. Firstly, I want to give you an introduction to Overstock and the sponsored ranking problem at Overstock. Overstock is a retail e-commerce marketplace for home goods that consists of products on sale put on by our partners that users interact with. These partners also bid for particular placements on the website. The sponsored search experience consists of showing multiple items that are paid for by advertisers to users. In this context, a good ranking function is able to satisfy demands of all parties involved, that is, the needs of the platform, user, and advertisers. We implement a ranking strategy that aims to optimize for all three of these explicitly. As the platform implementing the bid optimizing for advertisers, we leverage additional information across both demand and supply side to provide an optimized ranking to benefit all parties involved. The classical sponsored ranking ad rank formulation is bid times the expected click-through rate, but this does not sufficiently address both the long-term goals of the advertisers, which is to get sales for their products, and the goals of the users, which is to find products they're interested in. The landscape for sponsored search is very dynamic. The participants in a sponsored auction are determined by the goals and the availability of advertisers, and these may vary with each campaign and over each day, and by budget availability during any specific time. This makes reinforcement learning-based approaches attractive. But applying reinforcement learning to sponsored search has been underexplored, primarily due to the dilemma of exploration. Random exploration can be prohibitively expensive for sponsored search ranking. In practice, we can't do exploration online in production due to potentially incurring significant revenue loss while exploring. We aim to address these concerns in our paper. In 2018, we observed a similar approach at AdKDD presented by Hay. We build on this work, leveraging the same ranking strategy and the actor-critic based approach to sponsored search ranking. We preserve the actor-critic formulation for comparability, and in this paper provide design decisions for the environment model based on intuitive principles that are agent agnostic and eliminate the need for hand-tuning of parameters. Hay 2018 presents a ranking strategy that incorporates a function of click-through rate and the bid price to optimize for the platform revenue, monotonic nonlinear projections of click-through rate and conversion rate of the user, and a function of item price and conversion rate to optimize for the advertiser, and learn scalar A variables to balance the weights of these three terms. The click price is derived from the second price auction mechanism as the smallest price that is sufficient to maintain their allocated positions in the search results. Finally, the reward for the reinforcement learning agent is computed as the predicted click price times the CTR for the product. To minimize the cost of exploration for reinforcement learning, we leverage the observation that previous user engagements are highly predictive of the next engagement behavior. Hay 2018 outlines the inconsistency posed by not having such a sequential model, and therefore the need for an online model on the learned ranking function for their formulation. From a user modeling perspective, previous user interactions have high predictive power, and thus problem formulations that model the sequence of user interactions have demonstrated high performance in search and recommendations. From a sponsored search perspective, this potential for user engagement serves as a decision point for whether to participate in the auction and at what price, and these sequential decision-making steps for a potential reward lend themselves well to reinforcement learning. This idea has been explored by Wu, presented at Wisdom 2019, by adopting GRU RNNs to model the user behavior sequence. We employ a similar architecture, trained on user behavior sequences to serve as the simulated environment for exploration by the actor-critic model. This facilitates better effectiveness and consistency between the reinforcement learning goal and the exploration task by increasing the expressive power of the model. We formulate the learning of the sequential environment as a regression of the prediction of the click price to the real price using a square loss. We derive the predicted click price as the minimal price required for maintaining its current position in the general second price auction mechanism, combined with a scaling parameter that is a nonlinear projection from the hidden state S of t. This parameter helps calibrate the range of click prices leading to the predicted price as outlined. This formulation allows us to capture the sequential information of user behavior into the simulated model and makes the learning signal more precise, since the model can now update itself by learning from the real click prices. We further improve the environment model by ensuring that the environment model can cleanly separate positive and negative samples, ensuring consistency of the learning goal and aiding interpretability of the model. Intuitively, a desired environment model should be able to provide distinct signals between advertisements that are more likely to be clicked and those that are not, given a particular context. We clip the prediction of the click price and therefore the reward for the reinforcement learning agent for positive samples to be in the positive range. In addition, we then encourage the A coefficients that combine the different optimization objectives in the ranking function to always be positive by adding a normalized term based on the A coefficient to the reward. This helps mitigate the vanishing A coefficients that were caused by overwhelming negative signals the agent receives that tends to push all A coefficients close to zero. We observe that it is possible for the reward signal to be negative, and when this happens, the reward signal cannot be kept consistent with the learning goal. To see this, consider the case when the click price prediction is less than zero. To keep consistent with the monotonic nature of FA requires that we decrease the A coefficients when the advertisement is negative. However, due to the A1 coefficient being part of the denominator of the reward function, the agent can increase the reward by increasing the value of A1. This undermines the agent's ability to learn the reward consistently. We remedy this by a further treatment on the negative samples with negative rewards, by ensuring the denominator of the click price is not dependent on the A1 value, and instead amplifying the value subtracted from the numerator for negative rewards. This causes the agent to decrease A1, which is consistent with the learning goal. This allows us to consistently connect with a CTR-based model as the base case. Finally, we use a standard deep deterministic policy gradient with a 25-layer policy network and a 2-layer value network, similar to Hay 2018. We avoid the use of any heuristics on parameters of the model, making it easier to test across different domains. In addition, we do not have an online function update. Because our changes pertain only to the simulated environment and the reward signal, and are agent agnostic, we believe this provides a fair comparison across approaches. To compare our results to our existing approaches, we ran this model against production logs from overstock.com. We used a week of production auctions to train a model, and then we evaluated by running the auctions from 1 day of production logs. We simulated clicks and calculated click NDCG to compare rankings. We compared several different ranking approaches. Here, we see that the worst ranking would be to rank the ads by bid. The best of our current rankings would be to rank by expected click-through rate. Note, ad rank in this table is our current production ranking. Our reinforcement learning model using the new environment model, outperformed all of these ranking approaches, as well as the offline model presented in Hay 2018. We also see that multiple epochs of training the new environment yields improvements on click and DCG, thus validating the effective of the new environment. This graph compares the reward of our reinforcement learning approach using a trainable environment against the approach in Hay 2018. We see consistently higher rewards and see a lift in reward from running multiple episodes. Overall, we see significantly better average rewards and better ranking performance when compared to other approaches based on real-world production logs from Overstock.com. In the future, we plan to focus on real-world deployment of the reinforcement learning model. Although we don't want to incur the risk of live exploration in production, we are investigating various approaches to near real-time exploration, such as doing exploration in offline batches several times a day. I thank you for your time. My name is Nishan Subedi, and I presented work with Chen Wang and Aidan Finn. Please reach out via email if you have any questions, comments, or feedback, or are interested in working on these problems with us. Overstock is hiring machine learning scientists for sponsored search ranking and a variety of other problems. Thank you.